All right, hello everyone. So we have a calculus question here. Find any horizontal asymptotes for the function f of x cosine of x plus 8 root x divided by the square root of x. Okay, so first of all, when we're looking for horizontal asymptotes, we need to find the limit as x goes to infinity or the limit as x goes to negative infinity. It's really an and or, depends on the domain here of your function. So not all the time will you be able to find the horizontal asymptotes if you have a domain restriction for which you can't, you have a bounded interval, we say, meaning that you can't go to infinity or negative infinity, then you have that type of restriction on there. We couldn't take these limits. So for this function, if you notice, you have a square root of x in the numerator and in the denominator, okay, as terms. And if you recall, with the square root, you can't take the square root of anything that's negative. You can plug 0 in, that's fine, but not anything negative. So first of all, our domain is going to be restricted to nothing that's negative. So this part right here where I ask you to find the limit as x goes to negative infinity here, we're not going to work with that at all because we can't do that here, okay, because of our domain restriction. Another thing about the domain restriction is that you can't actually plug 0 into this function, because if you plug 0 in, the denominator would be undefined, okay? So your domain here, let me just write it out, for this function would be 0 to infinity, or we prefer to say x greater than 0. So the only type of asymptote horizontal asymptote we can look at, is by taking the limit as x goes to infinity. There are no other restrictions on our domain except for x is greater than 0. All right, so let's go ahead and take a look at that limit here. So we have the limit as x goes to infinity of cosine x plus 8 root x over root x. And if we were to take this limit, there's a few ways of doing this. However, what I'm going to do here is, my intent, as the title suggests for the video, is I'm going to use the squeeze theorem here, okay? And for me to apply the squeeze theorem, there's a couple ways of applying it here, but I'm going to do this. I'm going to first of all split this function up as the cosine of x over root x plus 8 root x over root x. Okay, we're allowed to do that. That's a property of fractions. So the numerator can be split up into multiple parts all over the same denominator is what we're saying. And if we take a look at the function furthermore, the part where I have an 8 root x over root x, that can be simplified by canceling the root x's out. You just get an 8. And furthermore, we can split this up as a sum of two limits, the cosine of x over the square root of x plus the limit as x goes to infinity of 8 here, as long as both of these limits exist, okay? The limit of as x goes to infinity of 8, that's just 8, so that stays. However, what's this equal to? And you might have a good idea what this limit is equal to. Cosine itself, goes between -1 and 1, and root x just gets really large as time goes on. So my guess here would be, I think that this limit's going to be 0, okay? But let's prove that rigorously, and that's where the squeeze theorem is going to come in. So let's talk about the squeeze theorem. And the squeeze theorem says something along these lines. You have three functions here, so you have h, f, and g, and if h of x is less than f of x, which is less than g of x, for x in an interval containing a. So basically all that means is that you have one function is less than another function, which is less than another, and you have for an interval containing a number a. So basically it means that this order that you see here for the inequalities doesn't have to be true always. As long as it's true for an interval containing a, this theorem works out. And the theorem says this: if you take the limit as x approaches a of h of x, which is the smallest function, and if you take the limit of the largest function on that interval. As x approaches a, and this a could be infinity, and you get the same limit L, then the limit of the middle function has to give you L as well. Okay? Graphically, this is what we're looking at. And the reason it's called the squeeze theorem is because f of x is the green function here. That's being squeezed in. Here, let me move this. F of x is being squeezed in between h of x, which is the amber golden color, and g of x, which is the red function. And the idea is, like, as you approach a here, both h and g approach the same value L, whatever that it might be. And therefore, because f is squeezed in and it has no choice, it'll be squeezed in. Sometimes it's also called the sandwich theorem. Okay, all right. So that's what the picture says here. Now, how does that actually work for us here? Well, and applying it. So I'm going to go ahead and we're going to figure out, again, the limit as x goes to infinity of cosine x over root x. But let me start off by working with an inequality. And why is that? Because the theorem, the squeeze theorem, deals with inequalities. And sine and cosine lend themselves very nicely to inequalities. Cosine as well as sine is greater than or equal to -1 and less than or equal to 1 for all x. So this statement is true. And what I'm going to do is this. I'm going to now divide by root x. And when you do this, the inequality is preserved, because root x is always positive. For any number for which x is greater than 0, root x is always positive. You know, square root of 4 is 2, square root of 9 is 3, etc. Positive number. And so when you divide and multiply a inequality by a positive number, the inequality stays, it's preserved. If it was a negative number, then it's switched. And the gist here is you have you build up an inequality from some fact, and then you build up your function by putting parts into the inequality in the sense. And what I mean by the parts is like, real detailed word there, right? I mean, you put the parts in the function. So for example, that the root x that I was speaking of, that we have in the function, we put that into the function, into the inequality, as you see here. So you build it up, so whatever the limit that you're taking is of interest, you want to get that limit, basically, that function in the middle here. So I want to have cosine x root x in the middle of the inequality somehow, okay? And that's what we did. So again, we said to ourselves, okay, cosine of x is between -1 and 1, so you build up some inequality, often from some known fact, so in this case from trigonometry, and then you divide by square root of x in this case, and you get your inequality. And what we're going to do now is we're going to take the limits of the stuff at the end here. The limit as x goes to infinity of -1 over root x and 1 over root x here. And if you're looking at the notation that I was using before, you want to refer to that. This would be like your h of x. This would be your f of x. And this is your g of x, okay? And we're going to take, again, our limit as x goes to infinity, and both of these functions go to 0. Yeah, 1 over root x gets really large as x gets arbitrarily large. So 1 divided by something really big is nothing. 1 pizza divided by 1 billion people, not much. Pizza's going to get... people are not going to give it that much pizza. Nothing big, much is what we're saying. And the same thing for the -1 of root x, 0 on both. And therefore, by the squeeze theorem, because the functions at the ends gave you the same limit, the 1 in the middle must equal the same. So therefore, the limit as x goes to infinity of cosine of x root x equals 0 by the squeeze theorem. Okay? So the squeeze theorem really helps out in cases such as this, when you're trying to prove something rigorously here. It also works in cases where you have things that are like undefined. So for example, we have x times sine of 1 over x, not the limit, excuse me, I'm talking about a function and for which you're trying to find the limit of. For example, limit as x approaches 0 of x sine 1 over x. Yeah, you can't plug 0 in here. And you can't figure out what this limit is by just like plugging things in. And the only solution is like you really don't have any other analytical tools. The only way about to do this is by using a technique like the squeeze theorem. Okay. Well, and therefore, just to finish up our work, let me go back to what we had originally, what we're looking for, which was this limit. And we had 0 is what this whole thing became by the squeeze theorem, plus 8 is equal to 8. So your horizontal asymptote here is equal to y equals 8. Yeah, horizontal asymptotes are always equations, y equals a number. Okay. All right. Well, thank you for your time. Hope this helps.